Welcome to Math World. Today's class, let us learn one more operation on complex number, that is finding a conjugate of a complex number. The complex conjugate or simply the conjugate of a complex number, say z equal to x plus iy, is defined as the complex number x minus iy and is denoted as z bar. Okay, if z is a complex number x plus iy, then its complex conjugate or simply the conjugate is z bar. It is x minus iy. In fact, which is the reflection in the real axis of the point x comma y. See, when I have a plane, I mean a complex plane, real axis denotes x. Now, so this is the origin. If I take, say, somewhere point x comma y, that is z, a complex number z is here, then x minus y is the reflection on x axis or real axis. So somewhere here you will get x minus y. So this is z and this is z bar. If this is z, then this is z bar. So z bar is simply the reflection in the real axis of the point x comma y. We can observe few things, so let me list out them. First one, z bar is there. If you take its conjugate again, then that is simply z. See this, you can observe z is nothing but x plus iy. So z bar is x minus iy. So if I take one more times a conjugate, then that becomes x plus iy, which is nothing but z. I'm sorry. Yes. Now the second observation is mod of z bar is same as mod of z. This is true for all z. If I have, say, for example, if I have z equal to 1 plus 2i, okay, then I know how to find modulus of z, that is root of x square plus y square. Here 1 square plus 2 square, that is 4. So it's root 5. Now z bar is just the change of the value of the imaginary parts. So change of the sign, in fact, 1 minus 2i. So mod of z bar is again same thing, because irrespective of the sign of this imaginary value. So since we are taking a square, so it's coming out to be same. Therefore, I can say mod z bar equal to mod z. Next is the conjugate of the sum is the sum of the conjugate. Say for z1, z2, for two complex numbers z1 and z2, it says conjugate of the sum. In the sense, sum, I'm taking its conjugate. The conjugate of the sum is the sum of the conjugates. Sum of the conjugates. Similarly, the differences, if I have z1 minus z2, its conjugate, then that is same as z1 bar minus z2 bar. And one more, if z1 and z2 are two complex numbers, then z1 z2 to two complex numbers are multiplied, and then I'm taking a conjugate, then that is same as z1 bar into z2 bar. And one more I'll list out first and then we'll go for the explanation. z1 by z2 is there, and its conjugate is same as z1 bar divided by z2 bar, provided z2 is a non-zero complex number. And say when I have a complex number z equal to x plus y, if z equal to x plus iy, then real part of z is x, and I want to represent real part of z in terms of z only and imaginary part of z in terms of z only. Okay, I repeat, when I have z as x plus iy, real part of z is x, but I want to write real part of z in terms of z. Okay, so how to write that, and even the imaginary part of z. Okay, so let us find this. Yeah, z is x plus iy and z bar is x minus iy, right? So let us go for adding them, z plus z bar. So it's x plus iy plus x minus iy. Iy will get cancelled, so it is 2x. Therefore, I can write x equal to z plus z bar by 2. In fact, what is this x? This x is nothing but real part of z. Therefore, I can write real part of z as z plus z bar by 2. Okay. Similarly, I'll do subtraction. Z minus z bar will be x plus iy minus x plus iy, so that x will get cancelled and I'm getting 2iy, so that I can write y equal to z minus z bar, z minus z bar divided by 2i. What is y? Y is nothing but the imaginary part of z. So we can directly write y imaginary part of z as z minus z bar by 2i. So this thing you need to remember. If z is x plus iy, then the real part of z is nothing but z plus z bar divided by 2, and imaginary part of z is z minus z bar by 2i. This helps in solving many of the problems. Okay, we'll go for one more observation. That's, say when I multiply z with its conjugate, what I'm going to get? Let us find it out. Z is x plus iy and z bar is x minus iy. Okay, so this is equal to x square minus I into xy plus I into xy minus I square into y. So x square, then this will get cancelled. Minus I square is minus 1 into minus, so it will be plus y square, right? This is same as writing root of x square plus y square, and it's a square, isn't it? Yeah. Now what is this? This is nothing but modulus of z, right? It's square. So z into z bar is nothing but modulus of z whole square. Isn't it? Okay, one more observation. Mod z1 z2 is nothing but mod z1 into mod z2, and similarly mod of z1 by z2 is equal to mod z1 by mod z2, provided z2 is a non-zero complex number. You may get doubt why this is so and why this is included in the study of conjugate of a complex number. See, we know one thing, that is zz bar is modulus of z square, right? I'll just prove this. We have studied now mod z square is nothing but z into z bar, right? Now instead of taking z square, what I do is I'll take, say, z1 z2, it's a square. Okay, now the square is same as, I'm sorry, here it must be, okay, now this is same as writing z1 into z2 and conjugates of z1 z2. Okay, thus we have observed z1 z2, its conjugate is nothing but conjugate of z1 into conjugate of z2. Okay, so I'll do that. This is same as z1 into z2, and this is z1 bar into z2 bar. It won't matter much. Now I'll club this with this and this with this. So z1 into z1 bar and z2 into z2 bar. What is this? z1 into z1 bar, that is nothing but mod z1 square. Similarly, this is mod z2 square. This is same as writing mod z1 into mod z2, it's a square, right? So you can in fact say simply mod z square is same as writing mod z square, right? If in this case, suppose I have z1 equal to z2, then z1 into z1, right? So it's mod z1 square. If you want, I'll write it down, one second. If z1 equal to z2, then mod z1 into mod z1 equal to mod z1 into mod z1, right? Then this is nothing but mod z1 square equal to mod z1 whole square. That's what I'm saying. Mod z square equal to mod z whole square. Mod of z square is same as mod z square. Similarly, the cube mod of z cube is same as mod z cube. So now we'll go for a problem. Show that z bar plus 3i and its bar is z minus 3i. If z is x plus iy. Okay, z bar plus 3i is x minus iy plus 3i, right? So x plus I into either, yeah, I can write it like this, 3 minus y. Y. Now I want its conjugate, z plus, z bar plus 3i. Its conjugate, it must be x minus I into 3 minus y. So this is same as writing x minus 3i plus iy. So this is x plus iy minus 3i. So that x plus iy is z minus 3i. X plus iy is z. So minus 3i. One more. Problems are a bit easier if you know the properties. Show that modulus of 2z bar plus 5 into root 2 minus I is equal to root 3 into modulus of 2z plus 5 if z is equal to x plus I y. See, now you observe one thing here. We know modulus of z bar is same as mod z its bar. Okay. And one more thing is there. This is same as modulus of z. You can take any example for z and you can try this. Okay. Modulus of z bar, because you are getting a, see, z bar means if it's any complex number, then you are getting a constant over here, a value, right? Mod z gives you the value. The same thing applies over here. That will be equal to a number and its conjugate. It will be same. Similarly, it will be same as modulus of z, because z bar means you're just changing the sign of the imaginary number, but when you take a modulus you are taking a square, so value won't change, right? So this you need to remember, and the same thing I'm applying over here. Okay, now modulus of z1 z2 is equal to mod z1 into z2. I repeat, modulus of z1 into z2 is equal to mod z1 into mod z2. Same thing I'm applying over here. So the left hand side is can also be written like this, modulus of 2z bar plus 5, I'm so sorry, into modulus of root 2 minus I. Now this is same as writing 2z plus 5 its modulus, and modulus of this is nothing but root of root 2 square is 2 and minus 1 its square is 1, right? Yes. Now modulus of z bar is same as modulus of z. So this is same as writing 2z plus 5 and this is root 3. The same thing is here, which is same as right hand side, root 3 into modulus of 2z plus 5. Next problem, sketch the set of points determined by the condition modulus of 2z bar plus I equal to 4. See, sketching is easier if we can rewrite this condition in the form z minus z naught equal to r, right? So have to rewrite this condition in this form so that we can decide whether it is a circle, ellipse or whatever. Okay, so let us go for rewriting this. Okay, the condition is modulus of 2z bar plus I equal to 4. See, we know mod z equal to mod z bar, right? The same thing I'm applying here. Modulus of 2z bar plus I, taking this whole as a complex number, this is same as writing this as 2z minus I equal to 4. In the sense, conjugate mod of conjugate is equal to conjugate of its mod, right? So side, rewrite over here, 2 into modulus of z minus I by 2 equal to 4. So this is same as writing z minus I by 2 equal to 2. So this is in the form z minus z naught equal to r, where radius is 2 and the center is at I by 2. That's the point 0, 1 by 2. So let us sketch that. I by 2 comes out to be here. Okay, this is I by 2 and radius is 2. Okay, you take from this, so space is not enough for me. It's okay. Just roughly I'll draw. I'm drawing a rough sketch. Okay, center is at I by 2 and this is the radius, which is equal to 2. Okay, we'll go for the next problem. Show that modulus of real part of 2 plus z bar plus z cube is less than or equal to 4 when mod z is less than 1. In fact, less than or equal to 1. See, we know from triangular inequality modulus of z1 plus z2 is less than or equal to modulus of z1 plus modulus of z2. Same thing I'm applying over here. Okay, so this left hand side is equal to, in fact, less than or equal to mod 2 mod z bar plus modulus of z cube. When mod z is less than or equal to 1, of course its conjugate and the mod will be less than 1, and mod z cube, same as writing mod z cube, and since mod z itself is less than or equal to 1, so this will also be less than or equal to 1 cube, in the sense 1. Okay, so this will be less than or equal to 2 plus 1 plus 1, so which will be less than or equal to 4, which is the right hand side. One more problem. Show that the hyperbola x square minus y square plus 1 can be written as z square plus z bar square equal to 2. See, this can be written like this, in the sense I need to replace x and y by z and z bar. So what we know real part of z is nothing but z plus z bar by 2, and imaginary part of z is z minus z bar by 2i, right? This is nothing but x and this is nothing but y. I want x square minus y square. So x square minus y square. X square z plus z bar by 2, its square, minus y square z minus z bar by 2i square is equal to 1. Now this is z plus z bar square divided by 4 minus z bar square divided by 4 I square, so I square is minus 1, so this will be 1. Now you rewrite z square plus z bar square plus 2z into z bar, I'm sorry, plus z square plus z bar square minus 2z into z bar is equal to 4. Now these two will get cancelled and I'm getting 2z square plus 2z bar square equal to 4, which is same as writing z square plus z bar square equal to 2. So I'm rewriting this in terms of z and z bar. Okay, that's all in this video. In my next class I'll explain one more way of writing complex number, that is polar form. So far we studied Cartesian form, we used z equal to x plus iy so far. Now we will write z in terms of polar form, or one more exponential form. So that I'll take it in my next video. Thank you.